It's coming up. All right, so let's go back. We're gonna talk about mass spec today. Oh, I meant to upload this. Let me do that now because this is not on Blackboard. Blackboard that I know of. All right, so I just put a document in the chat. Uh, that this is it's the same document that we're working on, so you might want to go ahead and download it real quick. Um, or you can take a screenshot of it, however you want to do it. But the actual document is here in the chat. Um, so we're gonna go back and just go back and kind of review a little bit of mass spec, and then we're gonna look at some problems where we actually have to work through like the fragmentation patterns and all that stuff. So first question asked about the following is generated in a mass spectrometer prior to fragmentation. What would that be? Before any fragmentation, what's the first thing that happens after you bombard a sample with that electron beam?
Is it C?
You're close, but C would be actually a fragment. The base peak is a fragment, and this is prior to fragmentation.
Is it D?
So it's the radical cation. It's the radical cation is I'm just gonna say if I start out with CH4, right, and I hit it with this electron beam, that's gonna kick out one electron from that molecule and give me this, right? So that's prior to fragmentation. So any before any fragmentation happens, any pieces break off, you get this radical cation, which then becomes the species that gets fragmented. And when it fragments, one part of it is going to be the radical, and the other fragment, whatever it is going to be the cation. All right, let's look at the second question. It says, what question does mass spec answer about a molecule?
B.
B. It answers about the molecular weight, size, and molecular weight. What is CH framework? What method do we use to determine the carbon hydrogen framework? Right. We talked about four different methods for characterization, even though there are multiple methods, but we talked about these four. Right. So mass spec is here, is size and molecular weight. What about the CH framework? What method answers that question? We got either mass spec, infrared, UV, or NMR. Wouldn't that be NMR? All right. What about C? What answers questions about conjugated power systems? And your choices are, but obviously mass spec is out, NMR is out, so infrared or UV.
Is it UV?
UV. What does infrared tell us? What information?
Functional groups.
What functional groups are present? Good. All right. Um, let's go to the next question. Which of the following patterns do amines undergo? And this is based on what we talked about on yesterday. Not yesterday, I'm sorry, Monday. What's one of your major fragmentation patterns when you have functional groups like amines, alcohols, carbonyls? I need some Jeopardy
Is it
music
B?
playing. No, it's not B. It is a type of cleavage though, but it's not B.
Is it A?
All right, so amines, like down here, that's an amine, right? It undergoes what we call alpha cleavage, where the bond adjacent to it would cleave. So you'll cleave here, right? On the other side, you don't have anything to cleave where the CH3 is, but you'll cleave right there. So this is the position that's alpha to that functional group right here, that carbon. So all amines, alcohols, carbonyls, sulfides, I mean, you can go down the list of functional groups. They're all going to undergo alpha cleavage as one of the main fragmentation patterns, right? So alpha would be immediately adjacent. So over here, this is a CH3. So if I can get my alpha halfway decent, right? So you would cleave there, right? So that's any functional group that has a carbon adjacent to it, it's going to undergo alpha cleavage, right? So basically, let's look at the fourth question because it's asking that what fragments from alpha cleavage of the following molecules, it says draw them and give their masses. So we need to know the mass of this entire compound. So let's see, we
Or
got one. Go ahead.
is this worksheet on Blackboard? I can't find it.
I just uploaded it to the chat.
Okay, I was just wondering if it's on Blackboard.
I said that when I was uploading it. That is not there. That's why I put it in here.
Sorry.
That's okay. So how many carbons is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons. So let's add up. Let's do some math. And then we got 2 oxygens. And then 3, 6, 7, 9, 11, 13, 15, 17, 19 hydrogens. That's 120, 32, 19 is 171. Is that right? So the total mass is 171 grams per mole for that compound. If I injected a sample of that into a mass spectrometer, what would the parent peak be for that compound? So what the if you look at a mass spectrum, we talked about this Monday. What does the parent peak represent?
The molecular weight.
The molecular weight. So for this compound, the parent peak will be where? Will be at 171. What would the M plus 1 peak be?
172.
172. So that's my parent. And then 172 which is my isotope peak, it will be my M+1 peak. All right. So how many fragments? Let me. I'm gonna not say that. Well, I'll ask it. For this compound, how many alpha cleavage fragments are we gonna get? So we got a
Is it
alcohol here. Go ahead.
4?
You're gonna get 4 fragments. You got it's gonna because alpha cleavage is gonna take place at the alpha position of each of those functional groups. Right. So we're gonna cleave here and here. That'll be 2 fragments, based on what alcohol is, and then we'll cleave here and here. Right. And those 2 fragments will be based on the ketone, on where the ketone is. So we'll get these will be my fragments. I'm gonna draw them in different colors. Keep in mind when I cleave here, when I cleave right here, and I break that bond, that carbon that's right here, that's a CH2. So it's going to be a CH2 over here. All right, so that's going to be a fragment. And then on the other side, I'll have all of this stuff that's left here, like that. And this carbon right here is a CH, so it's going that hydrogen is still going to be there. That's a common mistake when doing mass spec. Is sometimes if you fragment a molecule and you don't count the hydrogen, then the mass of that fragment is going to be off. So you got to make sure you count that. All right. So that's that. And then for this side is 3 carbons. That's 36, and then a CH3, so 3, 5, 7 hydrogens, so 36. So this would be 43 grams per mole, right? So then all we have to do now is just subtract that from the parent, and we'll know how much the other fragment weighs, which would be what 127 is 171, so 128. Is that right? So 128 grams per mole for that piece. Are y'all following that? So that would be alpha cleavage at that site, and then if I cleave the other side, I'm going to get two different fragments. Let me see something. Shrink this down so I can make some room. All right. So what would the other two? What would the fragmentation look like if I cleave this bond right here? Right. You can see that, right? So those would be my 2 fragments. So I would have this, not that. And keep in mind that hydrogen is still there. And then I'll have that, right? So for that fragment that contains the alcohol, let's count that up. So 1, 2, 3, 4 carbons, that's 48. 1 hydrogen is 49. And then 2, 4, 7, 56 plus 17 is 73. So 73 grams per mole for that fragment. What about the one at the bottom? If we just subtract that from the parent, then we can get the mass of the bottom fragment also. Would it be 99? Is that right? Right, so 99 grams per mole for that piece. To total, it has to total up to the mass of the whole thing, which is 172. So you're not losing any atoms. You're just breaking bonds between atoms. All right. Let's go on that other end. Uh-oh. All right. So down here, you're going to cleave here. So that bond right there, because that's alpha. So you can see what your two fragments look like there. And then you'll cleave on the other side. Which will be right here. So those will be your two fragments right there. Are y'all following that or no?
Yes.
All right. So let's look at the second molecule. All right. I need a volunteer to do the alcohol alpha cleavage. Keep in mind, like, so this is alpha right here. That's alpha and that's alpha. So this is where you're cleaving, here and here. Let's see if we can total this up too. So 1, 2, 3, 4, 5, 6, 7, 8, 11. So 11 carbons. You got a OH. I'm just going to add up the OH. That's 17. And then NH2. That's 16. So we're just going to keep those intact. So 11 carbons, you got an OH, you got an NH2, and then you have, and this is in grams per mole, and that's 11 carbons times 12. I think that's 132. Right, and then if you count up all the hydrogens, you have, for the two terminal carbons, that's 6. And then you have 1, 2, 3, 4, 5, 6, 7 CH2s. So that's 14. And then 2 CHs. And so we got 22 hydrogens. So that's 132, 22. That's 154 plus 33, which would be 187. What would the M plus 1 be for that? If the parent is 187?
188.
188? All right. Any volunteers for that alpha cleavage on the alcohol? I feel like I should have added this up prior to class, like a cooking show, so we could already have the number. But it's all gravy. So if I cleaved to the left of that OH group, what would I have left? If I cleave right there, I would have that, wouldn't I? I'm gonna make that my radical. And then the cation will be all this stuff that's left. That's a lot to draw. I'll just write it in. I'll make that the cation, right? Because when I'm cleaving is the radical cation. So one fragment is going to be the radical, other fragment is going to be the cation. So this is the CH3CH2 is 29, and that means the other fragment is what?
It'll be like 159.
158. Yep.
Oh, 158.
It's graving. 158. Right, grams per mole. All right. And then if you cleave the other side, you're going to get two more fragments. So you're going to get a total of 4 fragments for that molecule. So on the let me go to the next page because I actually want to come back to the mass spec. I'm gonna turn y'all loose on the other fragments for that one, and then number 2 down here at the bottom. But let's look at this top question. So we have some infrared stretches up here, some absorptions, right? We need to match them to the functional group. Which one is going to match the alcohol? Right here. What do you think? Of those 4 stretches that are given, which one do you think is going to match the alcohol?
The third one?
The 3500?
Mm-hmm.
Yep, I agree with you on that. All right. What about the alkene right here? All right. What about the alkene? Now, the alkene and the carbonyl are going to have similar stretches, but the carbonyl is going to be, they're not going to be identical, but they are similar. And sometimes they do overlap.
Is it gonna be 1680?
1680. I agree. Uh, but so for the alkene, we can say that that one is going to show up at 1680. While you unmuted, where would the carbonyl be? See, they're both pi bonds, right? So they're going to absorb in the same area. So if the alkene is at 1680, then just logically, the carbonyl is going to be in that same range. All of your carbonyls, ketones, esters, amides, uh, aldehydes, they all absorb in that range, somewhere between 17, 1800. Right, so that carbonyl is going to be that's going to be your stretch at 1700. And then the last stretch is the ether stretch, that CO single bond stretch. We only have one left, right? It's going to be at 1150. That CO single bond stretch is always in that range between about 1,000 and about somewhere between 1,000 and about 1,200, somewhere in that range. All right, if you watch the infrared video that I sent out last week, it had that tape. There's a table in there with all the stretches on it. But the main ones, the important ones, I actually went over like on each one of them had a slide dedicated to it in that video. And the CO single bond is one of them. I think the only one we haven't seen again, other than in that video, is like the nitrile, the triple bond N stretch, and that's something like 2,200 or something like that. But other than that, we've seen all the rest of them. All right. So I'm going to break y'all out into groups. I want y'all to work on uh, this problem right here. Right, you already have the radical cation, so now it's just about fragmentation. So my suggestion is to find your functional groups, and we talked about alpha cleavage. We also talked about for alkenes allylic cleavage. So wherever that allylic carbon is, which is in this case going to be here, that's where your cleavage is going to take place. All right, and then you can also have alpha cleavage on the other side of that chlorine. The only thing we haven't talked about is right here, and we can do it right now. So the M+2, I think I mentioned it, but I didn't really go into detail. Right, that's only when you have a halogen present. So if you have a halogen present, you're going to get an M+1 peak as well as an M+2 peak. Again, dealing with the halogen isotopes that are naturally, available. So whatever the molecular weight for that compound is in the second example, you're going to get a M+1 for that and an M+2 because of that chlorine. All right. So let me set the groups up. If you don't join a group, we'll put you in the waiting room because that means you eating cooking breakfast or changing your oil or something, but you ain't in front of your computer or your phone. So let me set the groups up. I gotta stop sharing. You can go ahead and screenshot that if you need to, but I'll put the document in the chat again, just in case somebody didn't get it. All right, so I just uploaded that document again, but if you are on your phone and you can't see the document in the chat, then you can take a screenshot of the problem. But I want you to read the problem. Right, so it says calculate the molecular weight, so you know how to do that. Add up all the atoms. If you have to use a periodic table, don't be ashamed about that. Use it. That's why it's there. It says give the values of M+1 and or M+2. The only one that's going to give you an M+2 is going to be the second one. And it says give the fragments that you would expect from each of the following molecules when they're subjected to mass spectrometry. So you'll get here either alpha cleavage or the cleavage I just told you about, the allylic cleavage. All right. So I'm going to break y'all out for about 10 minutes and don't be all muted. Talk. That's the purpose of doing the breakout rooms. It's not a break room. It's a breakout room. So make sure you're having a conversation about these problems. Let's see. Here we go. Let me see. We got 33 people. So I'm gonna say 5 rooms. That's about 6 people. All right. So you should get an invitation to a room. Again, if you don't join, then I'm gonna just move you to the waiting room because that means you're not here, unless you're in the restroom or something like that. All right, we got 4 people who haven't joined. You need to find your breakout room and join it. What did you get for the first one? How many fragments?
2.
2 fragments. And are you able to annotate the screen or no? Where'd you cut it?
Yes, I
Okay,
can annotate it.
show me where you cut it for the first. Okay, good, good, excellent. So you ended up with these 2. Oh, my bad. These 2 fragments right here, right? CH3. We're gonna make that the radical plus. We'll make that the cation. Come on, Russell. All right. Good. Did anybody do the second one?
I did.
Move it back to where it was. That's close enough. All right. So for the second one, where'd you cut that one?
I cut it on both sides of the CL.
Yeah, I mean, I gave y'all the one side, so you cut it here as well, right? What was the molecular weight of that?
132.
So 132. So the M+1 would be what?
133.
133.
133, and then the M+2 would be
134.
134. Good. And that's what you will see in that mass spectrum. You see it. The M+2 is probably going to be really, really, really small, right? It's not going to have a high intensity, but it definitely will be there because you have a halogen present, right? And then the M+1 is always there. It's small too because of the natural abundance of that carbon-13 isotope, but it's there. All right, so you got 2 fragments from here. What about the last one?
I cut it on both sides of the OH.
Okay, so here and here. And what was the mass?
116.
All right, so all you need to calculate the mass is the atomic mass of each atom, right? Hold up, what's this question? Oh, no, it's not a question. Never mind. All right, we're gonna stop right here. For Friday, there's one other thing I want to talk about with mass spec, but it's not problem based. It's more like application. And then I'm gonna introduce you to the reactions that we're gonna cover for the last part of the class. And yeah, we only got like I think 2 or 3 weeks left, and we're done. So that's gonna be a blessing to be able to cross the finish line. So yeah, we'll come back on Friday, and if you have questions before then, you can just email me, set up a Zoom appointment, or however you want to do it. All right, everybody good? Did everybody get the handout from the chat? I'll post that handout, a blank one, in the course notes folder on Blackboard. All right. If everybody, if it's all good, I'll see y'all on Wednesday. I have a great afternoon or a great rest of your day.
Thank you. You too.